Welcome to another video on Circuits Decoded. This will be the first video in the new mixed signal series where I'll be mainly talking about ADCs and other mixed signal blocks. Today we'll talk about metastability in ADCs. It is a less discussed topic and one that is increasingly becoming important as high-speed ADCs are in higher demand today. Now we all have some idea about comparator metastability. Metastability occurs when the input of the comparator is close to its threshold. For such an input, the comparator's regeneration time is much longer and the following logic outputs an invalid or a random bit. However, today our focus will be how this comparator metastability impacts the ADC's output. Particularly, we'll talk about Flash and SAR ADCs. Let's try to define the metastability of a comparator first. Shown here is a simple comparator stage with a preamplifier gain of A followed by a latch stage. Depending on the polarity of Vi minus V threshold, the output of the comparator will either go to VDD or to ground in an exponential manner as shown in the waveform on the right. We can define valid logic level as any voltage above VDD minus V threshold to be logic 1 and any voltage below the threshold to be logic 0. The region in the middle is undefined. Now the time it takes for the comparator to reach a valid decision level is called the regeneration time or T range as shown in the diagram. The exponential relationship between T range and V0 can be written as shown here, where tau is the time constant of the latch. We can see that since Vin is close to 0, the initial value of the differential output of the latch is also near 0. Now, usually in a design, a fixed time is allocated to resolve a bit. For example, a flip-flop may be sampling the output of the latch at the rising edge of a clock as shown here. If the clock edge comes before the minimum required time, the output of the flip-flop is undefined, which gives rise to metastability. In other words, we can say that a range of voltage exists within which any input will cause metastability. The condition to metastability can be derived from the VFS equation and is shown here. A metastability window can then be defined as twice of this value, considering both positive and negative inputs. It can be seen that a higher preamp gain and a smaller time constant can make the metastability window smaller. The simplest example to understand the impact of comparator metastability is a Flash ADC. Shown here are the thresholds of an n-bit Flash ADC with m comparators. The threshold voltages are uniformly spaced to cover the entire input range. Now each of the comparator will have its own metastable window around this threshold value as shown here. The metastable window magnitude is assumed to be the same for all the comparators. Also, it is assumed that the input voltage has a uniform probability distribution, meaning that all the input samples in the range has an equal probability of 1. The total probability of metastability is given by this equation. Here, MW over Vref is the probability of metastability of each comparator. But since there are 2 to the power n minus 1 comparators and the input can be anywhere, the probability for all the comparators add up, and so P is given by m times MW over Vref. This equation can be rewritten in terms of the input full scale as shown below. This is also known as the bit error rate or the BER. The BER is an important metric in data communication and is influenced by a host of factors, one of which is metastability. Okay, we understand what the probability of metastable event is, but what is the magnitude of error if such an event happens? For a Flash ADC, it is easy to see that a metastable event will cause only one LSB error in its thermometer coded output. But the error may be larger when it propagates through the encoder. However, there are techniques to limit the error to 1 LSB, like gray encoding, which allows only one bit to change at a time. From the BER expression, we can see that if we are to keep the BER fixed and increase the resolution or speed, either the gain A must increase or the time constant tau must decrease, or a combination of both to keep the ratio constant. Now let's move on to metastability in SAR ADCs. We need to first understand its basic operation. So if you're not familiar with SAR ADC, this will give you a general idea of a SAR working principle. The figure shows a block diagram of a basic SAR ADC. There is a comparator, a capacitive DAC, and some digital logics that drive the DAC depending on the output of the comparator. The relationship of the DAC voltage with the digital bits is shown here. Wi is the weight of each bit and is shown in this table. The SAR logic tries to find the closest approximation of Vin for the DAC in a binary search method, and this happens in n clock cycles, meaning that for a 3-bit ADC, it would take 3 clock cycles to get all the 3 ADC bits. This progressive approximation can be clearly understood from the timing diagram of the DAC. We take example of a 3-bit ADC, and the input ranges from 0 to VREF. Assume that first there is no metastability or noise in the ADC, and the input sample is just below the mid-range, which is VREF by 2 in this case. The bit trial proceeds by setting the MSB or bit 1 to 1. This would set the DAC voltage to mid-reference point or VREF by 2. At the first clock cycle, the input minus the DAC is compared by the comparator. Since Vin is less than the DAC voltage, B1 is reset to 0. At the same time, bit 2 or B2 is set to 1. The DAC voltage is updated at the falling edge of the clock, and according to this equation, the DAC voltage will be Vref over 4. Now, at the next clock edge, the input is again compared with the DAC voltage, and this time the input is greater than the DAC. So B2 is retained at 1, and subsequently B3 is set to 1 for the next bit trial. This adds Vref over 8 to the DAC voltage. The final DAC voltage is then 3 Vref over 8. Now since Vin is greater than Vdac, B3 is unchanged, and so the final ADC output is 0, 1, 1. Now let's consider the same ADC conversion with metastability, and assume that the input is within the metastable window in the first bit 1 trial. So Vin is close to Vref over 2 as shown. Also assume that the comparator takes more than 1 clock cycle to resolve such small inputs. So in the first cycle, B1 is undefined, and the DAC voltage can be anywhere between Vref over 4 to 3 Vref over 4. The reason for this is as follows. Since B1 is between VDD and ground, the switch that connects the B1 DAC capacitor to the reference voltage is neither fully off or fully on. So the DAC voltage can be anywhere between 0 and Vref over 2. Also for the next bit trial, B2 is set to 1. So VDAC has an uncertainty from Vref over 4 to 3 Vref over 4. In the next comparison, however, the probability of another metastability is very small, since now the comparator input is more likely further away from the mid-reference point. However, since VDAC can be either positive or negative, the comparator output is still random. So B2 can be either 1 or 0. Now by this time, the SAR logic has resolved bit 1, and B1 settles to its correct value of 0. Also in this cycle, B3 is set to 1 for the next bit trial. So we can see that a DAC can have 2 levels in this cycle, 3 Vref over 8 and Vref over 8. But both levels are below the input. So B3 is retained at 1 in the next clock cycle. The first level is the correct level, while the later one is much further away from the correct value. The resulting code error is 2 LSPs. In fact, the error amplitude depends on the location of the metastability error and is given by this equation. In our example, J1 is equal to 1, so the magnitude of error is Vref over 4. In addition to the error magnitude, we need to find the probability of a metastable event. For this, we need to identify the number of possible comparisons at each bit trial. In this 3-bit example, we can see that in the first bit trial, there can be only one comparison. In the next, there can be 2 comparisons, and in the last, there can be 4 comparisons. So the number of possible comparison is a function of the bit location and is given by 2 power of j minus 1, where j is the bit number. This multiplied by the normalized MW gives the probability of metastability error. So we can see that the probability is higher for the later bits or the LSPs. But the error magnitude is inversely proportional to 2 power of j, so the error magnitude is lower for the LSPs and higher for the MSPs. This is the reason that sometimes the error for the LSPs are ignored as they can be designed to be below the noise floor. However, the MSB errors cannot be neglected as they can result in big glitches in the ADC code. There are a few strategies through which the metastability error can be addressed. Can you think of any? Please let me know in the comments below. So that's it for this video. If you liked it, please share and subscribe, and I'll see you in the next one.